So, we saw the Chevallier's theorem and Harishchandra's theorem, and we did use just recall yes. So, we have this Z lambda. Lambda is a linear form, and for every z in the center of the, this is the center of the universal elementary algebra, z acts by a scalar. So, psi lambda, chi lambda of z times v equal to z times v for every z lambda. And we showed that if we showed that chi lambda is equal to chi w of lambda plus rho minus rho whenever lambda is an integral weight, and for every w in the while group, where rho is the half sum of positives. And Harishchandra's theorem says that if chi lambda equal to chi mu, so at this level lambda mu are only linear forms, need not be integral, then some w in w. But anyway, finally, we are going to use only when lambda and mu are integral. We do not really worry when lambda and mu are not integral. So, in that sense, one should be happy even Harishchandra's theorem holds only for lambda and mu are integral. But anyway, this is true for any two things. Now, we are going to use this theorem, Harishchandra's theorem, and of course, the converse for integral weights to prove. So, today's goal is to prove Constant's multiplicity formula and Weil's character formula. And I have to say a few things about Prudenthal's formula and Steinberg's formula as in the part of my thing what is assigned for me. But I really do not worry if I can't do it today now, because there are two tutorials for me. So, I can do them. I want to at least concentrate on Constant's multiplicity formula and Weil's character formula in this lecture. So, what are they? So, first thing is, let me recall the notation. Alpha positive. So, this is the Q, the Weil function. So, you remember that I wrote some set of all functions, so having some property that their values are bounded by finitely many lambda i's, and P, the number of non-negative number of sequences k alpha of non-negative integers such that sigma k alpha p of lambda, p is a function, p belongs to chi, of this is minus lambda. And capital P, same thing with plus lambda at the end, same thing with plus lambda at the end. Here there is a minus. So, this is the constant partition function. I have proved some few of things in the last lecture about Q, P and other things. I will have to of course use them. Is it comfortable that I can simply carry on, or can I recall all of them? It is not too much of time. So, P is so there are things like P equal to product of f alpha. So, where f alpha on k alpha is 1 whenever k is a non-negative integer and 0 otherwise. So, this is one point, and we have also this epsilon 0 minus epsilon minus alpha, f alpha equal to 1. And finally, I mean whatever, the most important thing is that, let me recall those two things. The Q is nothing but epsilon minus rho times product of epsilon alpha minus 0. I would have written plus rho and 0 minus alpha, but you can do it that one also, because this is a minus half alpha, then it becomes a plus alpha, plus half alpha and a minus half alpha. So, that term is appearing here. So, you could see it from there, because rho is the sum of positive roots. And this is one of the main thing, I mean, that I want to use, and the another. So, the third and fourth are very important. The fourth thing is that I think it follows from some of these things that this is epsilon rho, because you see, you can see from this point of view, it's 1, and finally you are getting this thing. Okay? Not this one, plus rho and then that. So, that will be plus 1 and rho. So, this is 1 every time. So, I get epsilon rho finally. And the fifth thing is that CH Z lambda, this is the character of the formal character of the Verma module, is Q star. So, this is P star epsilon lambda. This follows from the freeness of the universal algebra of eta minus, the nilpotent radical of that on the highest maximal vector. These are the things. Okay. So, the things that I am going to use, possibly from this also you have something. So, this we can have. So, this Q star CH Z lambda is equal to, from here, this is epsilon lambda plus rho, because we have this thing which is same as P star Q star. So, this is epsilon lambda plus rho. So, Q star P star of that, which is that one. So, now we prove one lemma, and in the second lemma we use these things to deduce the first, of course, both formulas will come. So, lemma 1, the first thing is that let lambda be the star, then the first thing is z lambda has a composition series of modules of the form, I mean, with composition factors of the form. 1 V mu, so this is the irreducible ones, mu less than or equal to lambda and mu is of the form awesome W in the value. This is the beautiful idea that this part comes from the Harichandra. So, this is the point where Harichandra is being used. And second thing is of course, the multiplicity of V lambda is in lambda is 1. So, by this I mean in the composition series the factor V lambda appears only once. So, okay. So, we just give a sketch of the proof of that. So, this is more or less, this the proof is by induction on the number of maximal vectors. The number of maximal vectors is finite, follows from Harichandra. The thing is, because if you take a maximal vector here, then there is a homomorphism from Z, say of weight mu, then there is a homomorphism of from Z mu to, so there is a from a homomorphism from this that to Z lambda with that UG that maximal vector. So, with some weight, not mu plus some vector whose weight is mu, so maximal vector. So, but then by Harichandra we know that but then the center acts by same scalar by a scalar here, therefore, I mean by the same scalar here, but these two scalars are same, that means chi lambda equal to chi mu, that means lambda and mu are connected by this way. So, therefore, there are only finitely many, because the W of that one, and for each weight the dimension of that by the universal helping algebra argument of the eta minus, that will be the dimension is also finite, each multiplicity. Therefore, there are only finitely many things involved. So, we can use induction. Okay, so how do we use induction now? I mean, so the first thing is this part is clear, because V lambda plus is a unique this thing. By the definition, every weight of this is strictly, except that highest weight, every weight is strictly less than lambda minus sigma mi alpha I. Therefore, this multiplicity is unique, that we have seen many times. So, now, so if Z lambda is equal to V lambda, that is, if it is irreducible, then there is nothing to prove. I mean, this is how the argument in the book goes, but I do not see, I mean, maybe lambda is 0, is that lambda equal to V lambda? I do not have, I am not that good at, I mean, are there any, I do not believe that, but anyway, this, however, the argument works without whether examples are not there or not. So, Z lambda equal to V lambda, then there is nothing to prove. Otherwise, let V1 be a proper UG submodular of Z lambda, not okay. Clearly, I mean, so once it is proper, clearly V1 cannot contain. It cannot contain. Yes, it cannot contain. Because otherwise, it will be the whole thing by cyclicity. So now look at. So then, V1 must have a maximal vector, say V. This is because you can use this theorem. Okay, find dimensional. Otherwise, you can use the weight arguments. Since lambda is maximal, any weight is and any weight therefore is less than or equal to lambda minus sigma I my alpha A. Start with the weight, and you can keep on add some finitely many positive roots again and again. Then at some point that weight, there will be a weight whose mu plus alpha will not be a weight for any simple root alpha. So such a mu, of course, will exist. So therefore, such a maximal vector exists. Okay. So now you consider this module V, submodule which is U or UG of V, this thing. Then you have the map from so call the weight weight of V, say mu. Then you have Z mu. To this you have by the universal property of the Verma module, you have this surjective map, and so now we have two things, Z lambda by this V and V. So we have two modules. They have the property that each can be written as direct sum of weight spaces with respect to the action of the Cartan subalgebra, and every weight of these two modules are less than or equal to lambda. Of course, here it is less than or equal to lambda, and here is strictly lambda also. And the center of the universal Lyapunov algebra acts by the same scalar chi lambda of Z on both modules, because it is true for this as well as this. So, and note that here the multiplicity of course, the multiplicity of the weight lambda here is 0, which is less than that. So, I can use induction, and the multiplicity of the maximal of a weight mu is of this is less than the multiplicity of mu in the full module, because there is a mu already here. So, by induction, both modules have composed in series, and they have this property by Harichandra's theorem that chi lambda. So, whatever weight that satisfies this condition. So I think I gave enough explanation for this. Due to time constraint, I cannot write everything, because it is the last lecture, and I have to go into constant participant, constants formula now. Okay. So maybe I can write here. It's a constant. Formula. This one is okay. So, So now onwards we don't bother about general linear forms. We are strict to integral forms and also dominant. Okay. And mu be another. So this is okay. This is general. Of course, otherwise it could be 0. Otherwise that could be 0. It is not in pi lambda. Then the multiplicity. So this means the multiplicity of so notation that denote the multiplicity of the weight, or in other words, if we use this notation, it is much simpler. V lambda, the dimension of so if this notation is defined, I could do it. I think this notation is defined. Okay, so this is dimension of V lambda sub mu. So this is now the formula says m lambda of mu is equal to, then we have sigma minus 1 to the power length of w in the while group p of so this time I am using okay, so w of mu plus rho minus of w of lambda plus rho. I used to make the mistake, but I think now I have written correctly that that capital P is the partition function. So, I am always interested in the partition function. So, I was trying to write this way, but this is the correct if I use this function. Okay. For example, this is not non-negative always, you can see even when put single case, because this will be less than. So, but if I put the difference, it's always I mean in some cases, most of the cases is non-negative. So, so this mu is there, and of course, the rho is the opsum of positive roots and w is in the while group element. So, this is the okay. So, now we use this to so we prove this formula now. Prove. So, first thing is we have from this point of view, we have Ch lambda is equal to, I mean this notation is character of V lambda. This is equal to sigma C mu C h z mu less than or equal to lambda, mu is equal to w of lambda plus rho minus rho for some w. And of course, C mu are where C mu are integers. So, C mu are integers. So, this is the character of the Verma model. Mu running over weights less than or equal to lambda. Of course, I have lambda dominant. Mu equal to w of lambda plus rho minus rho for some w running over all those weights less than or equal to lambda and of the form this one. Of course, in the dominant case, I mean you could say you could ignore some of them, but anyway. Now, this part comes from that lemma, because Z lambda has a composition series with modules of this form, and I use that, but I do not give full details. This is the idea, and whenever mu appears here, that has that property. I mean, I may not be using only once, maybe every time I have to use z mu and then v mu like that, because here what is written is only with mu, but I am writing z mu. So, probably you have to use that also. Okay. Anyway, not only for lambda, every time mu you have to use z mu and v mu and the connection. But anyway, that way, using that, now we note a couple of things. So, look at this character of the character of this one. This there is a, see, of course, the Weyl group acts on the weight lattice, also on the entire H star, and this is equal to C h of lambda, the character of that, because this entire, I mean, it is a G module, and you know every multiplicity is also preserved by the Weyl group for the V lambda. So this would be, so what I am saying is this is something like if you write sigma some A mu E mu, then you apply this, these are linearly independent, and when you use that way, I mean, so this is sigma, but this is same as sigma A mu or A sigma of mu and then E mu. But then you know that multiplicity says that this is same as A mu. Okay, you could put here and then, but that is same as E mu, the multiplicity. So that way that they are equal. I do not mind repeating the proof also, it is very important. This is a beautiful idea, this simple argument, going to be repeated again in the Weyl's dimensional formula, that the number of positive roots made by negative, see what happens when you apply W to the definition here, then you have to apply epsilon W alpha by 2 minus W alpha by 2. If it is already positive, you do not ignore, I mean you can ignore, but if it is negative, you change the sign, then this becomes positive. So that remains all positive roots. So only a matter of sign, but how many times it changes is as many as the number of positive roots made by negative under the element W, but there is exactly the length. So that is why that minus 1 to the power length W comes. So this proof, I mean such a thing will be repeated in the Weyl's dimensional formula. So I am going to use that again. Such an argument, what I am saying. So this, therefore, using that and this, so look at this Q star C h lambda here. So which I think using this, we have C mu, so this is same as Q star sigma C mu C h z mu, but this is same as sigma C mu Q star P star epsilon mu by maybe I have not written here, it is there. So Q star P, therefore it is epsilon lambda plus rho, epsilon mu plus rho, sorry, it should be mu here, and epsilon mu plus rho. And note that this there is there's only certain mu's. Okay, so there is a notation if you want theta lambda. So I would say what is theta lambda? All those mu's, mu less than or equal to lambda, mu's of the form W lambda plus rho minus rho or some W. So this is a notation because we have seen that. So mu in theta lambda, and this is C mu, and from those two arguments you get this is C mu epsilon mu plus rho, this one. Now I told a couple of things. One is that the character of C h lambda is W invariant. The other one is that W q is this one. So I use so So, on LHS I apply W on LHS equal to minus 1 to the power length q, sorry, length W, sorry, so W times q star C h lambda, because this is W invariant and this is signature by that one. This is equal to RHS. So, this side we have sigma C mu epsilon W of mu plus rho, and of course mu in eta lambda. One small thing, but very important thing which I missed out here, but it is there in the argument. I mean I missed out in writing, but it is there because it is there here, that multiplicity is 1. So, this says something here with C lambda is 1, it says that. This is a very important thing, even though it is it's very important. C lambda is 1 because only once. So, this says that now we are coming to the. So, this side we have this side we have this, but this is nothing but again I rewrite the same thing here, minus 1 to the power length W sigma C mu epsilon mu plus rho. Now, compare the coefficients on both sides, and because epsilons are linearly independent, and use the fact that C lambda is 1, then what we get is, so this implies we have q star C h lambda is equal to minus 1 to the power length W epsilon W of lambda plus rho, and this is over the Weyl group element. The reason is because any mu, okay, first I look at the coefficient of C lambda on both sides. I mean the epsilon lambda plus rho, epsilon lambda plus rho. Epsilon lambda plus rho here will be 1, but when you do W inverse, this becomes minus 1 to the power lambda W times 1. So, that is why I get the signature there, that side. Yeah. And there are no more mu's here, because every mu is in theta lambda. So, that is if you write the equation is W of, in this side W inverse of lambda plus rho minus rho. So, W of lambda plus rho minus rho, that is why I get cancelled. So, I get again of that form. So, there are no more mu's. So, this is one of the main today I use this equation, this thing, and from here immediately if you use the partition, the constant partition, that small p function on the both sides, then you get the formula. So, apply p on both sides. Then what we get is P star Q star C h lambda, okay, and also epsilon minus rho on both sides. So, let us look at this side, but this is same as C h lambda, because P star Q star epsilon minus rho. So, P star Q star epsilon minus rho is epsilon rho minus epsilon minus rho, which is epsilon 0, which is the unit element of the that chi. So, here therefore, this becomes so, but this is same as coming to the so, what we are applying is only P and this thing. So, this side you get minus 1 to the power length W. So, look at here, if I apply to a weight mu, so up to this part I just leave it. Now apply to a weight mu, CH lambda of mu. So, this is nothing but here I have applied P star epsilon minus rho star sigma minus 1 to the power length W epsilon W of lambda plus rho of mu. But this is same as, of course, this is simply additive, here there is no problem. So, P star sigma minus 1 to the power length W epsilon W of lambda plus rho minus rho of mu. But now you see the partition function, so these are all epsilon, the characteristic functions. So, they assume value only at those points. So, then if I want to apply a P here, then this should be mu minus this one. That is where mu plus rho minus W of lambda plus rho, that comes here. Mu minus of W of lambda plus rho minus rho. So, I get that is exactly that. So, that is exactly that. So, we are done. Maybe I would have kept this. Okay. Okay, so now so this formula is proved. Now the corollary, the immediate corollary to this is that Q is minus 1 to the power length W epsilon W of rho W in the. So, this is really good that we are actually getting an element in lambda. I mean, the Z is actually in lambda. So, not just in the, okay, of course, this is sitting inside here, but it is actually here. Looks like that half and all it comes here in the definition of Q, but now it is actually here. So, how do we prove that? Take lambda equal to 0 in star. We take lambda equal to 0 here, this side of course is clear that RHS is that side, and this side is Q star CH lambda, CH 0, but B 0 is one dimensional, lambda equal to 0 the linear form, the irreducible representation is one dimensional, and the character of course is only one character, which is epsilon 0, and that is the unit element. So, Q times 1, which is Q. Okay. So, this is a simple but beautiful thing. Now, Weyls character formula. I mean, it is actually Q, but I write in terms of this to see the elegancy. I just rewrite the star, I just rewrite the star with Q equal to that, that is all, that is the Weyls character formula. So, in particular you see the nice thing is that this by this is always a genuine element of this one. I mean, a priori it is not clear that this element divided by this means actually is as a formal element. So, that becomes because this we know this is an element here, lambda is a dominant integral. So, it is a finite integral linear combination of certain weights, and therefore, this is clearly a element here. So, this by this. So, that follows from here. Okay, so, just here. proof is already there. I mean, I explained. Once the things set up, proof is there. What I told is Q I rewrite and the star already we have proved. So, proof is already there. So, one nice thing we use the we can use this theorem to prove dimension on that says so the dimension of lambda. So, rho is again the upsum of positives. So, lambda plus rho by comma alpha divided by rho comma alpha. Okay. Okay. So, to prove the theorem, first thing is that we consider the chi 0 subalgebra of chi. So, this is all those functions and at star having the property that the support is contained in finitely many, I mean in the union of weights of the form of this form for finitely many lambda i's, but now for various lambda i's. But now we are considering only the subalgebra of chi generated by epsilon lambda in lambda, all lambdas. Okay. This is something like in the class functions you take only the virtual characters. In the class functions you take the virtual characters. Okay. Finally, there, but there that's equal, but here they are not equal. These two may not be equal. Now, here we have one for each positive root, define an operator on for every thing here, every f here, or just to extend by epsilon lambda is equal lambda alpha epsilon lambda in lambda, and extend this by on this entire thing by derivations. And I have, so let me say one property about this one just quickly. So, if we look at product of all when these things has compositions, then this this of any epsilon lambda is equal to, so every time we are doing, so this is product of lambda alpha alpha positive times epsilon lambda. This are going to, so the special thing will be interesting when lambda equal to rho because of that. And we have this valuation kind of thing. So we have to see the functions. So they have we add the values. So this is sum of the v of any. So if it is of the form sigma a lambda I, lambda I. So this is sigma a lambda I. So the sum of the values it is defined. Now I use this and the formula to prove the wide dimension formula. So what I do is first look at this thing on LHS of Weil's character formula. Now see, this is product of all del alpha running over all positive roots. Here, if you ignore one of the, see, one of the d alphas, so this is a composite sense. Okay, so it's like d beta 1, d beta 2, etc., d beta r in some ordering. Say, if one of the positive root is missed out here and it's applied here, this is the composition. Every time it's a derivation. Okay, then here that okay, yeah, we have to use something. This one is epsilon W of rho. So this is Q's already. Q which we have already seen. This is epsilon minus rho. Epsilon minus rho. So this we have already seen. Positive. And you could think of this function as the function 1. I mean the constant thing epsilon 0. So if I apply the I mean as an element of the group ring, this is 1. So if I apply the this operator at least one times to the right here, then the entire product of all of them not applied here. So that means one of them will survive here, but then the sum will be 0, because how many times the coefficient appear here, the negative of that will appear here. So the sum will be 0. So that dou will, I mean, so finally what we are getting is on the left side, so dou of LHS is equal to dou of this one epsilon W of rho CH lambda, because every time it's a derivation. Because at least once if it's appeared here, I say it's 0, one of the d alphas. Okay. So every time, so what we are getting is this. Now using this and apply further V, then you could see what is V of CH lambda. So V of CH lambda dou of V of dou of this thing this is in W is same as V of sigma minus to the power length W epsilon W of lambda plus rho. So, this is what we are getting now. So, I could write this number as this by this. So, this is exactly the dimension of the V lambda. So, this by this is what I want, but you see here the dou that I have written, this side is V of this is product of so the sigma minus 1 to the power length W. So, this we have already seen, this is product of rho alpha, alpha positive, epsilon epsilon sigma alpha. Okay, that is a small thing, but it is W rho. See here, I will quickly do this one. V of sigma minus 1 to the power length W plus length W. I will tell you why there is one more length W here in a short while. That is why I kept explaining that part. W on Q is minus 1 to the power length W Q. There is an argument. You see how many times the sign comes. Here you see this is rho comma W inverse of alpha. This is rho comma W inverse of alpha. Okay. And there are some certain alphas, W inverse of alpha still remains positive, and for certain it will be negative. But what remains is only a sign. The number of positive roots is same. So, then but how many times the sign comes here? It is as many as the number of positive roots made by negative under the element W inverse, because W inverse. But that is same as the number of positive roots made by negative under W also, because the lengths are same. So, that is why I put 2 times. But then I should change here rho comma alpha, alpha positive, epsilon W rho. Okay, and then there is a V outside. But you see, therefore, this becomes so this is V, but every time it is plus. So, this is simply the while group, the coordinate of the while group, and then the product of rho alpha, alpha positive, epsilon W of rho. This is same as. So, this is simply the valuation map. So, every time, so this is 1. So, what I am getting is simply the alpha, alpha positive. And you see, just look at that. So, here this is what I am getting with the order of the while group, with order of the while group. But now do the same thing here. What is the same argument? V of minus 2 to the power length W, product W of lambda plus rho, there is no W of lambda plus rho alpha, epsilon W of lambda plus rho. But then that W inverse is again, and the same number of negative roots, because W is not changed. So, it is 2 times, and lambda plus rho alpha, epsilon W, lambda plus rho. So, what I am getting is again, but finally, what I am interested in, not that epsilon, this is a basis. So, every time it is 1. So, finally, this number, but then here lambda plus rho comma alpha. So, that is in the numerator, because this by this. So, therefore, we are proved. Is that okay? So, we have proved the thing. So, just I think I have time, I can talk about Freudenthal's formula and Steinberg's formula, but since I was beginning, I was saying that I want to concentrate on Constant's multiplicity formula and Weyl's character formula. I am obliged to say one more thing about the Weyl's character formula as in the learning process, that there are more fundamental works done regarding the Weyl's character formula, but the most among the most thing is and most it looks elegant and elementary. In that sense, I am obliged to say that there is a formula simply using operators. So, can I say that? I mean, I am obliged to say that as a fundamental thing, but it is out of syllabus, but as it is not very complicated to say also. That is why I plan to say that. It is very elementary in that sense. So, take any alpha I as simple root. Simple root. So, look at this notation m alpha I. This is a map from z lambda to z lambda. Okay, take sending of course is on the basis. So, this is e power lambda, and my notation e power lambda is a basis. This is e power lambda minus e power s alpha I dot lambda divided by 1 minus e power alpha I. Okay. So, this dot is of course the S alpha I dot lambda is this is S alpha I of lambda plus rho minus rho of some of positive roots. Yeah. Now, the idea is due to de Mazur. This idea is due to de Mazur. W an element of the while group, define MW. We can do it in the tutorial if need, that this is an element of here. I mean, there are cancellations, so that will get cancelled and we have to do with that. Okay. So, MW and say it is of the form S alpha I1, S alpha I2. So, reduced expression. Then you have M alpha I, M alpha I2. The thing is that MW is dependent of reduced expression, and in particular when you take W equal to W naught, consider W equal to W naught, the longest element of the while group, longest element of the while group. Then we have this M W naught of and now let lambda be dominant, m w naught of E lambda is C H lambda. So, the Weyls character formula, the C H lambda has another form. So, if you keep writing like this, we could we could get like this. What we can do is, if we have time, I could do it for SL2 on both sides. So, that will be a good thing. So, let us recall the here suppose case 1 lambda of H I is non-negative. So, then what we get is E lambda minus E, say the number is m, and this is E lambda minus m plus 1 alpha divided by 1 minus alpha I. So, this is same as take E lambda outside. So, this is 1 minus E minus alpha I to the power n plus 1 by 1 minus E minus alpha I. Therefore, this is same as E lambda 1 plus E minus alpha I plus e power minus m alpha I. This is same as E lambda plus E lambda minus alpha I, E lambda minus m alpha I. So, this is the thing when in the first case. In the second case, lambda of H I equal to minus 1. So, here E lambda minus, this is also E lambda, in that case m alpha I lambda, this is 0. And then the third case is lambda of H I is less than or equal to minus 2, then one equal to e power lambda minus e power, say this is minus m. So, this is S alpha, which is so lambda minus of so there is a plus m alpha I plus m minus 1 alpha I divided by e power 1 minus e power minus alpha I. So, what I do is now could do with this. So, there is a minus sign change, and then you could write e power lambda m minus 1 alpha I minus e power lambda divided by 1 minus e power minus alpha I. So, this is same as minus e power so this you can take it outside. One plus etc. plus. So, this is one less, which is up to. So, this is e power. Okay, I will write directly what is the answer. So, this is better. E power lambda plus alpha I this you can check. So, it starts from one above and then goes there. So, now our case is interesting case, this case we are in the dominant lambda is dominant. So, we always have this situation, and we are in SL2 now. So, only one simple root, and we have to check that this is same as that one. Mostly I think it is. See. So, what we have, so this is the that formula we have. So, therefore, this is the the character of the. So, just recall from here. In SL2, and there is dominant CH lambda e power lambda plus e power lambda minus alpha plus e power lambda minus lambda h alpha. There is only one h, so I write hi, only one h lambda minus. So, this is same as, of course, this would have been mentioned in SL2 already in the workshop. It should have been done that way, but here now if we use this one. So, here there is only one row here. I mean, there are two elements here in the while group. So, this is epsilon w. So, this is only two elements. So, this is epsilon rho minus epsilon w rho, and rho is here of alpha by 2, and this is S alpha, this side, and we have CH lambda, and this side we have this one, which is epsilon lambda plus rho minus epsilon S alpha lambda plus rho. This is what we want, and this side what we have is epsilon lambda plus rho minus epsilon lambda plus rho. So, this is call it m, lambda which is m. So, this is m plus 1. So, minus m plus 1 alpha. So, rho is again here alpha by 2. So, here is alpha by 2, and so here we have epsilon alpha by 2 minus epsilon minus alpha by 2. So, what we need is CH lambda is equal to epsilon lambda plus alpha by 2 minus epsilon lambda. So, this we can epsilon lambda we can take it outside, epsilon alpha by 2 minus epsilon m plus 1 alpha minus alpha by 2 divided by this way, and okay, this you could okay, we will do it in the tutorial. just type. So, this is same as that one. I will check it carefully and then We will do it in the closure. Okay. Can I state the Steinberg's formula? So I have time here. Lambda prime and lambda double prime be two dominant weights. Let lambda be another dominant weight. Then the multiplicity of V lambda in lambda prime is given by so this is again the constant partition function, not that the other one, the p with minus lambda. So you have this V lambda prime tends to be the lambda double prime is again a G module. Both are G modules. So for the diagonal action, it's again a G module. And how many times the Eurodis representation V lambda appears here? So there is exactly this much with the with this. This is the formula. And again, I mean, I would have mentioned a couple of things in the constant multiplicity formula and also here, that when in that formula when mu equal to lambda, you can check easily that except that I will explain first this and then come to that part. So, when you take lambda equal to lambda prime, lambda double prime, you can see that this number is 0 unless sigma equal to tau. I mean, what I am saying is, if you take lambda equal to lambda double prime here, when lambda equal to lambda double prime, then this lambda double prime plus 2 rho minus sigma of lambda prime, the sum, the full thing, then this plus 2 rho minus sigma, this one, this one will not have any this thing will not have any I mean the p of that is 0 whenever the p of that is p of that part 0 unless sigma equal to tau equal to identity. So, so it is a genuine in that sense. That's all I'm saying. So before saying this one, I would have mentioned that part for the constant partition, constant multiplicity formula, and so here the constant multiplicity formula was m lambda mu, so lambda is denominated here. So we have sigma minus b to the power w p of e plus rho minus w of lambda plus rho. So here also I have to say some few things. I would have spent more time on here. Anyway, I still have time. So what I want to say is when mu equal to some tau lambda, which is an extremal weight. I mean, in V lambda, there are finitely many weight vectors which are very important. The multiplicity of this is same as the multiplicity of lambda, because that is W we have discussed so many times. And the even there, it is not so easy to apply this formula to get that number is 1. Of course, when tau is identity, we can see, and like whatever I said, when tau is, when mu equal to lambda, if mu equal to lambda, then you can see that except for W equal to identity, it is, everything is 0, you can see that. So that says, that is, and also that is 1 also you can see, because P of 0 that one, so you can see that. But then, and there also that is true, P of, V lambda appear with multiplicity 1 in V lambda prime, tensor V lambda double prime, when lambda equal to lambda prime plus lambda double prime. So those two are, but when you take the tau, that is not a, there is not an easy thing to conclude. There are signs, okay, that is one thing. Another thing is that I know that for some reason, given this thing, nu in the z minus of z r plus, that is the sum of so minus sigma mi alpha I, mi is a non-negative integers. I can always choose a lambda sufficiently large, such that the dimension of V lambda sub lambda plus nu is same as dimension of z lambda sub lambda plus nu. I thought, okay, I intuitively I used the kind of the, I think a little bit geometrically, but I thought there could be signs coming there, but Viswanath pointed out that it can be done. He said that it is possible to have such a point, such a lambda without using signature. That means only the identity comes. Okay, then I went and checked that when you take lambda of hi is at least, okay, so if I take lambda of hi is at least mi, then I would be able to check that this is genuine in that sense. Okay, that's one remark. This is an exercise. What I mean is this at least for every I. So that is that's right. Whatever he said. So that way I have checked. And another thing is that I am interested in mu equal to 0. So this is precisely the T invariance. Mu equal to 0 is precisely the T invariance. So this is a even here even a special case would be really it is not easy to check. Very simple case, you take lambda, the notation theta is being used for highest root. The highest root, that is the highest weight of the Okay, this is a simple, G is a simple Lie algebra, simple Lie algebra, semi-simple is simple also, there is no, okay. So, that means the Dinghy diagram is connected, there are no. Then you take the highest root, there is the highest weight of the Lie algebra itself as a module. I mean, there are possibly there may be two highest roots, but I am looking at that root. Now, look at this, what is the, so what are the zero weights of, so V theta sub 0. So, what is the, so the dimension, so dimension of this. So, what is it? This is simply the dimension of the Cartan subalgebra, which is actually the rank of the Lie algebra. The zero weight space is exactly the Cartan subalgebra, the Lie algebra, rank G. So, even this number, and even again special if you want, I mean, we'll get, I mean, G is say SL and C. Even there, the using this number, putting mu equal to 0 and lambda equal to theta, the side is not, I mean, it's not easily computable. I mean, even that. Of course, this number is clearly, this is, I mean, this number, for example, in this case is n minus 1. When this is G is SL and C, this number is n minus 1. So, even there, it is not a single, I mean, you have to use again, but of course, not all Weyl group elements are coming into the picture, only certain of them we could do combinatorially that using Dinghy diagram, but the number is complicated. By the way, I was interested in this because I am studying the T invariance of the of certain ring which is connected to these things. So, that way I am interested in that. So, it is not clear. In fact, I want to know what are all, I mean, certain in the program, what are all the, which of the T invariants are exactly the polynomial ring. So, this is my interest. So, that way I got into that, I mean, mu equal to 0, but then I am considering certain rings, like for example, you look at V m lambda star dual. So, this is a graded ring, and here look at the T invariants. There is again a ring. So, this ring, when it is a polynomial ring, is the question. With Santosh, I have proved certain, I mean, if something happens, it's a polynomial ring, we have checked, but we believe that the converse is also true, but I do not know, if, I mean, trying to use this, I got stuck. So, that way it is not easy to use this to, I do not know if it is used to check even the, because polynomial ring has a nice multiplicity every time. I mean, the Hilbert polynomials are very nice. So, that way I do not know if such a thing can be used to see that. It's a nice formula, but when trying to apply it becomes very difficult. Yeah. So, even this case is very, this is the first genuine case in the module V lambda. Even there it becomes a problem. So, anyway, so we will look at some examples for in the tutorial, some examples for lambda equal to theta, and try to do that. It is a good thing if someone really do it for even completely for SLN, but only for theta, even not even multiple of theta is even really difficult. By the way, in SLN case, this is a polynomial ring. When run over all this is a polynomial ring. In SLN case, this is a polynomial we have checked, and in some other types also, but not all types. And yeah, okay. So thank you.